So in HPLC, there's a variety of different detectors that we can use for our detection of analytes as they're eluted from an HPLC column. And so we're going to go over a couple of those different detectors here in this video. So the first one that we're going to do is a diode array detector, or a DAD. And you'll notice that we abbreviate a lot of things, and so you'll see things hyphenated. So you might have an HPLC-DAD, and that says, HPLC is my form of separation, and DAD is going to be my form of detection. Now, a diode array detector, if you remember thinking all the way back to the beginning of the semester when we talked about spectrophotometry, we talked about diode arrays as a way to detect light changes in spectrophotometric measurements. And we're going to do basically the same thing here. This is kind of going to merge the output of an HPLC with a mini spectrophotometer tagged on the end. So like any good spectrophotometer, we're going to need, a light source, and we're going to use a mirror here. This is just a concave mirror. Oh, I can't draw. There we go. To direct this into our sample holder. Okay, so these come off, and they are going to come in. Now, our sample holder here is going to have internal reflectance, and that means that as the light hits the edges, it's not going to be escaping. Okay, so we have internal reflectance going on in what we would call our flow cell. Okay, so as the light comes out, we get this kind of directed it into our analyte chamber. Okay, so how does this analyte chamber work with our how our HPLC column works? Okay, so as we have our column, I'm drawing this small here just for the sake of room. But as analytes come off the column, they're going to pass into one end of the flow cell. Okay, so this is kind of our analyte in. And they'll fill up the flow cell and then be flown out to waste. And so the analytes are pushed from one end through the flow cell out to waste. While they're in the flow cell, the light is going to pass through that solution of whatever analytes are passing through the flow cell and interact with them. If they absorb the light that's passing through the flow cell, then we'll be able to see that at the end here. Because like any good spectrophotometer, we're going to need a couple of things here at the end. We've got an exit slit that's going to help narrow down our which light is going to be sent towards our detector. We're going to need, a mirror where we're going to be ultimately detecting or sending light down here. We're going to do a grating, which you remember is as the light comes down on these, it's going to be separated into its individual wavelengths. And each of those wavelengths is going to strike our photodiode array. Or PDA. Okay. So this diode array detector, remember we talked about it before, and we said you have this grating that separates them out afterwards. So you can use polychromatic light and still get individual wavelength information at the end that allow us to use Beer's law to quantitate the sample in the center, in the sample chamber. Okay, so as analytes pass through the flow cell, we're going to be observing the absorption of these wavelengths to determine when we have an analyte coming out. So when you see a stronger absorption, it's because that's from the analyte itself. So what are some really good things here? The first is that these aren't particularly expensive, okay? So a diode array detector is not an expensive type of end detector to put on our instrument, okay? But on the flip side, it's, not all analytes are going to respond to it, right? Our analyte has to absorb our wavelengths of interest, and that's not true of all analytes. Okay, not everything absorbs in the UV range. Remember, you have to have some kind of like pi electron, a pi electron configuration that's to really have strong absorption in the UV or visible regions. So this is not what we would consider a universal detector because we don't have all of the analytes responding to the detector. And not all analytes that respond are going to have equal intensities. At a given wavelength, remember you have the absorbance is equal to EBC, that's Beer's law, where this molar absorptivity is wavelength dependent. So you can have instances where your absorbance over time for the chromatogram, where we get an analyte A coming out and an analyte B coming out, and we might instantly look at that and say, oh, analyte A has a lower concentration than analyte B. But in reality, if the molar absorptivity of A is much, much smaller than B, these could actually be at equal concentrations, or even with A having a higher concentration, just because the relationship of Beer's law of absorbance is affected by the molar absorptivity. Okay, so just because one gives a higher peak of an absorption does not mean it is at a higher concentration when these are different analyte species. Okay, so keep in mind, while we can do quantitation using Beer's law, and that's really helpful, it can sometimes be misleading when you're just looking at two analytes themselves, trying to guess without having references to compare them to. All right, so that's the diode array detector. So again, we're not universal, but we are inexpensive. So our main advantage here is inexpensive. All right, so how about our next detector? So next we have a charged aerosol detector. This is a CAD, okay, so you might have an HPLC-CAD. And in a charged aerosol detector, we're going to use a nebulizer similar to what we used for our atomic spectroscopy unit, where we needed to take an analyte from the solution phase, hear what's eluting from our column, and turn it into a gas, because we need to be an aerosol, right? If we're going to do a charged aerosol detector, we've got to get it in aerosol, and we've got to do some kind of charging. So to get it into the aerosol, we're going to use a nebulizer that's similar in idea to what we used with our atomic spectroscopy. So here we are, our eluate, so this is from the column. We call that an eluate. And we're going to send that in here. We're going to surround it by nitrogen gas. And that interaction here, just like we saw with how this gas flowing around the tube here is going to help break these up into tiny droplets, we do the same thing here. Okay, so now we have our analyte in little tiny droplets. Okay, they're going to pass through a drying tube, and the drying tube is exactly what it sounds like. It's just here to help our analytes dry out, and so that they get smaller and smaller and smaller and smaller, and we get rid of a lot of all the solvent from that's left around the analyte. So we're just going to try to dry off that solvent. Okay, now we get these little aerosol particles, and they enter what we call a corona charging chamber. And so what does a corona charging chamber does? Well, the main purpose is just like it sounds. We're going to charge the analytes, right? We've got a charged aerosol detector, so we've got aerosol, now we need to charge it. And how this works, we have this little platinum needle here. And the nitrogen gas is going to get charged by the platinum needle. Okay, there's a high voltage applied. We're going to charge the nitrogen gas. So we're going to make N2 plus, okay? And so when we have N2 plus, this is then going to interact with our analyte. So we've got these positive charges, and as the analyte and the charged nitrogen gas react, now we get a charged analyte and our uncharged nitrogen gas. Okay, so we're basically going to charge the nitrogen gas using the platinum needle and then transfer that charge via collision to the analyte itself. So now we're left with positively charged analytes. All right, now we've got to do some kind of a detection for these. We're going to sweep them out. We're going to do a little trap for small ions. So we might trap any additional N2 plus that's lingering. Okay, and we're going to send this to a collector that's going to capture the aerosol particles. And as it kind of as they collide and are condensed, we have an electrometer that measures the charge in the collecting chamber. Okay. Now, what's interesting about this is that the response here is actually proportional to the square root of the mass of the analyte. So the mass will actually play a role in the level of response. Okay, so this is the charged aerosol detector. One of the perks of this is it does respond to all analytes. So it is considered a universal detector. And you get an equal response for similar amounts. Okay, so if you have a similar mass of analyte, you get a similar response. But the response itself is going to depend on the solvent composition, because it'll depend on if you're getting your full drying or not, and what kind of amount of solvent is left on the analyte when it hits the corona charging chamber. So as you're changing your mobile phase, it ultimately is changing the solvent surrounding your analytes coming off the column, and so you're going to get a more complicated response factor if you are using gradient elution. So we get a complicated response factor for gradient elution. Okay, so that's our second option for detectors. The next option for a detector is actually a technique in and of its own right. Much like spectrophotometry can be done by itself, but we can use that technique as a detector in a diode array detector. We can use mass spectrometry as a detector for a HPLC system, spectrometry. Okay. And this is abbreviated MS. Now we'll spend some time in the next module talking about this, so hang tight till our final module of the semester for a whole lot of detailed information. But in general, and to kind of precursor that, we would use something like electrospray ionization because we're starting with a liquid sample. And this is going to nebulize and ionize, and we're going to end up getting some information based on the mass to charge ratio. So that's really all I'm going to say about mass spectrometry, because we're going to spend 2 weeks on that shortly. Okay, the next option we have is an electrochemical detection, or an electrochemical detector, and this would be an ECD. Okay. In an electrochemical detector, we're basically doing a redox, a reduction, or an oxidation. And so this kind of detector is only going to be a possibility for analytes that can undergo oxidation or reduction. So you're looking at things like phenols, aromatics, ketones, aldehydes, halogens, all of those that have good lone pair electrons that can, or very electronegative groups that can be oxidized or reduced. Okay, so we're basically going to have an electrode setup, and I don't have a good sketch for this, but we're basically using electrodes, and the analyte will collide with them and transfer an electron. And that transferred electron is going to be registered as a current. So if you are doing, if the sample is oxidized, that means it's losing electrons. The sample is losing electrons. And so there is an increase in electrons at the electrode, and you see an increase in current. And for a reduced sample, it's the opposite. Reduced sample, the sample gains electrons, which means you're decreasing electrons at the electrode, and you get a decrease in current. Okay. So the electrochemical detector is pretty simple and straightforward. Again, it's not very expensive, but you are limited to only being able to analyze analytes that can be oxidized or reduced. We've got 2 more here. We've got evaporated, or evaporative light scattering. And this one's not as common, but it is still used. And basically we're doing the same process of nebulizing and evaporating, but then instead of trying to charge it like in a charged aerosol detector, we're actually shining light on it and seeing how the particle reflects the light. So you evaporate it out, you get your little aerosol, and as you shine light on it, that light is going to be scattered depending on the angle that the light hits it. And so you can get some information using detectors set up around the chamber about what angles that light is being scattered towards. This is also commonly used to a method to size the size of the particles, to kind of determine how big of particles we have. And so you can actually use that as a way to detect particles coming out of your coming out of your column, and also get some size information if that's how it's set up. And then the final one to talk about here is refractive index. Again, not a really common one, but for those of you in microscopy, you've learned about refractive index. We talked about this somewhat with the ATR crystal, about how different substances have light will move at different speeds through them. And so as analytes are eluting from the column, the the composition of that solution is changing. And so as the solution's composition is changing, the refractive index is also changing. And so we're looking at the Ri of the solution as the composition changes and measuring that over time. Okay, so again, I'm not going to sketch that one. It's not as common, but I wanted you to be aware of it as well. So there you have it. Some pretty uncommon detectors that are possible. Mass spec is a huge workhorse. We're going to talk about that a lot more in the mass spec module, where we're going to spend a full 2 weeks on that technique. And then some of the other ones, we have basically a spectrophotometer hooked up to it, and then a charged aerosol detector as well. So those are some of our options for detectors to use with HPLC.